Bismillah ar-Rahman ar-Rahim. Students, in this lecture I am going to tell you about the Boolean algebra. Another name of the Boolean algebra is the logic algebra as well, because this algebra operates on the logic circuits, and the variables what we have in this algebra may have two values only, 0 and 1. So it is why this algebra may also called logic algebra, because this algebra was developed by a mathematician whose name was George Boolean. So it is why this algebra was named after him. It is why this algebra is called Boolean algebra. And this algebra was invented back in 1852. But till 1938, there was not such use of this algebra. But in 1938, Claude E. Shannon has used this algebra in the logic circuits which were based on the relay elements. You know, relay is electromechanical switch. So it is a switch which can operate through electrical signals. We connect the electrical signal and then we make the mechanical contact. So the relays based logic circuits were using the Boolean algebra back in 1938, and it was done by the Claude E. Shannon, where you can see that this algebra was invented back in 1852. So this was a brief history about the Boolean algebra. Now we must know that how this Boolean algebra is basically implemented inside the logic circuits. You know that we have three basic gates. The very first is the AND gate, and the symbol of the AND gate is straight line with a curve here. And let's say we are talking about the two input gate, so we will having two inputs and one output. Every logic gates may have one, two or more than two number of inputs, but the number of input must be defined. And in my previous lecture I have shown you that why we may have the multiple inputs. Multiple inputs mean if there is a logical discussion having multiple arguments, so we may have the gate with the multiple inputs, because every argument then becomes the input for the logic circuit. But every gate must have single output. So it is why here you can see here that it is one output. Let's say I label the two input by X and Y, and the output, let's say I label the output by Z. So this is a two input AND gate. Now we can implement the Boolean logic identities based on these gates. Here you can see that, let's say the two inputs are same. If I make the two inputs common, let me write it here clearly. If I make the two inputs common and then I take only one input here, let's say this input is X. So what should be the output? Here you can see that this will give us one Boolean identity, and that will be X dot X. It means one input is X, another input is also X. This dot represents the AND operation. So what should be the output? Here you can see that if X is equal to 0, so input is 0, 0, both the inputs will become 0, 0, because the two inputs are connected with a single input. It is shorted together and it is further connected with the one input, and that input is named as the logic X. 0, 0, what should be the output? 0. What if we make X is equal to 1? The two inputs will become 1, 1. What should be the output? 1. So it means that X dot X is always equal to the value of X, which is equal to X. So it means X dot X is always equal to X. This is the first Boolean identity what we have derived based on the concept of the operation of the AND gate. Second, let's say I have one input X and the second input is permanently connected with the 0. By 0 mean physically it is connected with the ground. Now if the value of x is 0 or it is 1, because one input of the AND gate is 0, so output will always be 0. So because of this operation, we may have the second Boolean identity, and what is that? X dot 0, it means one input is permanently 0. Whatever the value of x is, output will always be equal to 0. So this is second Boolean identity, that what we can derive from the operation of the AND gate. Next, we may have this type of situation. Let's say one input is permanently connected with 1, it means it is connected with VCC or plus 5 volt. And the second input is x. One input is permanently 1. Now x may have two values, x is equal to 0 or x is equal to 1. If x is equal to 0, what should be the output? 0. And if x is equal to 1, what should be the output? 1. So it means in this case, output follows the value of x. So here we have the third type of Boolean identity, in which we have x dot 1 is always equal to x. Because if x is 0, output is 0. If x is 1, output is 1. So it means output follows the values of x in this type of situation. So in this type of situation, we may have this identity, x dot 1 is always equal to x. We may have another type of situation for this gate, and what is that situation? Let's say I connect one NOT gate here with this one, and now we have only one input, that is x. If x is equal to 0, so this will become 0, and through this NOT gate, the second input will become 1. What should be the output? Output will be 0. What if we make the value of x is equal to 1, so this input is 1, and through NOT gate, it will invert the output and this will become 0, again it is 0. So it means in this type of situation, one input is x, another input is x complement, because it is passing through NOT gate, so it is why it is x complement. So in this situation, the output of AND gate will always be 0. So it is why we have the third Boolean identity based on this type of situation, in which we have two inputs, x dot x complement. It is always equal to 0. So based on this AND operation, we may have these four types of Boolean identities. Now you have to remember about these Boolean identities, mean x dot x is always equal to x. This, because this is a Boolean algebra, this is not a normal algebra. In normal algebra, you can see that x dot x is equal to x square. But this is not a normal algebra, this is the Boolean algebra. So in Boolean algebra, we can see that x dot x is equal to x, x dot 0 is equal to 0, x dot 1 is equal to x, and x dot x complement is equal to 0. So these are the four Boolean identities what we have derived based on the AND operation or AND gate. Let me write it here. Next we have the second basic logic gate, and what is the name of that second logic gate? Yes, the name of the second logic gate is the OR gate. So we will write the OR gate here. Base mean you know about the symbol of the OR gate. The OR gate symbol mean in AND gate you have seen it was straight, but right now it is a curve, just like an arc, and we have another arc here, and this is a third arc. So this will make the OR gate. Now here we have suppose two input OR gate, one output is there. Again let me talk about in terms of x. Let I make the two input common and I connect one input with the name x here. So what type of operation we may have in this situation? Now in this situation you can see x, this input is x, this input is also x. If value of x is 0, both input will become 0, 0. What will be the output? 0. What if the value of x is equal to 1, both input will become 1, 1. What will be the output? That is 1. So now we may have the fifth Boolean identity, in which we have x, and you know that OR operation is represented by plus sign. X plus x is always equal to x. If x is equal to 0, output is 0. If x is equal to 1, output is 1. So it means output follows the value of x. So x plus, here by the plus mean or, x or x is equal to x. So this is the third Boolean identity what we have in case of the OR gate. Now let's talk about the same condition what we have taken for the AND operation. Let's make this input permanently equal to 0, mean connect this with the permanent ground and make it x. Now if value of x is 0, this is permanently 0, 0, 0, output is 0. If the value of x is 1, 1, 0, the output is 1. So it means output follows the value of x. So in this will gives us the sixth Boolean identity, and that represents x or 0 is always equal to x. So this is the sixth Boolean identity what we have derived based on the OR gate operation. Next, we may have this situation, and that if we permanently connect this input with 1 and make it 1, mean make it connect it permanently with plus 5-fold. Let's see what's happened to the second input. Let's say second input is x. Now if x is equal to 0, this is 1 and this is 0, 1, 0, output is 1. If x is equal to 1, so this is 1, 1, output is 1. So it means output is not following the value of x. It is always equal to 1 because one input of this OR gate is permanently 1. So with this condition we may have the seventh Boolean identity, and that is x or 1 is always equal to 1. So we have this type of situation, and let's talk about the fourth situation or condition in case of the OR gate. Let's connect the NOT gate here and make only one input here, x. This is x input and this is x complement input. So here mean we can see that we will have x plus or x complement. What should be the output? If x is equal to 0, so this input is 0 and this input is 1, and this is x complement input. So output is 1. If x is equal to 1, so this is 1 and this is 0, so output is 1. So in this case output is always 1. Output does not follow the value of x, so it means it is always 1. So x or x complement is always equal to 1. It is not like this. In case of AND gate, you have seen that x and x complement is always equal to 0, x or x complement is always equal to 1. So this is the situation, and you can see we have derived the eighth Boolean identity based on the OR gate. Next we may have only one identity based on NOT gate. And what is that identity? NOT gate. Look at this NOT gate. The symbol of NOT gate looks like this, just like a triangle with bubble here. This is input x and this is x complement. Now based on this condition, we may have that if we connect the two NOT gates in series, so if x enters here, this will become x complement, but when again it's entered to this will become x complement, that is equal to x again. So based on this, we have only one Boolean identity, x double complement is always equal to x. So we have this type of Boolean identity as well. So these are the 9 Boolean identities. Let me write this. It is based on OR gate. This is based on NOT gate. We have 4 Boolean identities based on OR gate, AND gate, and we have 4 Boolean identities based on OR gate and 1 Boolean identity based on NOT gate. So we will use these Boolean identities in Boolean algebra in order to simplify the bigger circuits into the smaller circuits. So with the help of the algebra, what we can do, we basically reduce the bigger circuit into a smaller circuits, or the more sophisticated circuit. The circuit having more number of gates can be reduced to a circuit having fewer number of gates without affecting the basic functionality of the circuit. Let's say we have a circuits having 100 number of gates, and if we apply the Boolean algebra and we reduce the circuit to maybe to 5 number of gates or 10 number of gates without affecting the basic functionality of that circuit. So if we able to reduce the circuit up to 90% or 95% without affecting the basic functionality of the circuit, so that is basically a big achievement. And how can we get this achievement? We can get this achievement based on the Boolean algebra. Now let me give you an example or the analogy of this type of that why we are going to implement our logic circuits into a Boolean algebra. Let's say you have to travel from one country to another country. So let's say you have a very cheap source and that is your foot. I mean you can use your feet and you can cross one country from one country to another country using your feet, or you can walk through. That is, that is a very big task in order to travel from one country to another country using your feet or through walks. There is another transportation means, and that is an aeroplane. If you sit in the aeroplane and you fly from one country to another country, so how easily you can shift from one country to another country? By using the very advanced means of transportation, and that is an aeroplane. So same is the example here. If you are given a logical problem and you are asked to reduce this logical problems or to recognize this logical problems or to identify the type of functionality in this logical problem, and if you don't use the Boolean algebra, so it will make your life very miserable, very difficult in order to identify that, because you have to go through that circuit many times, giving multiple inputs and then making different types of tables, and maybe after 1 day or 2 day or 3 days iterations, maybe you able to understand that what is the functionality of this, or what is the very basic function of this type of circuit, or maybe you able to reduce 20% or 30% number of gates, not 90% or 80% or 95% number of gates. Whereas if you put that logical circuits into Boolean algebra is a mathematics. So mathematics is very rich in terms of formulae and in terms of different types of theorems and lot of other relations. So if you able to model the logic circuits into a mathematical model, which is the Boolean algebra right now, you can easily reduce the circuit from the bigger circuit having more number of gates to a very smaller circuit having very less number of gates without affecting its functionality. So it is why we are here to talk about the Boolean algebra. And in this part of lecture, I have explained you that how we can make or how we can derive the different types of Boolean identities, because based on these identities we can reduce the bigger circuit into the smaller circuit. These identities will help us in finding the reduced or the simplified circuit having the prime state without affecting the basic functionality of that type of circuit. So these are few identities, and there are few more identities which the logic circuit obeys. I will just write that, you can confirm it yourself. That one is the commutative law. Commutative law. Commutative law, you know about the commutative law, that if we have two inputs x dot y, so it is exactly equal to y dot x. So if we change the position of the variables, so it will not affect the logical operation. And logic basically obeys the commutative law. Simply you can see that if the number of inputs, you just change the name, so nothing will happen to the basic operation of the gate. And you can exactly apply the commutative law based on the OR gate as well. This is commutative law on AND gate, and this is commutative law on the OR gate. So commutative law based on AND as well as OR gate, it obeys the law. Next is the associative law. So logic obeys the associative law as well. Let's say we have three variables, x dot y dot z. It is equal to x dot y dot z. It means if you AND the y variable and z variable first, and then you AND the output of this AND gate with the x input, it is exactly equal to this way. If you AND the x and y first, and the output of this AND gate is further AND with the z, so it is basically not disturbing the basic operation. So associative law, it obeys the associative law based on the AND gate as well as based on the OR gate. It is like this. So if you change the order of the input variables, so it does not affect the operation of the logics. Commutative law, associative law with AND gate, OR gate, AND gate and OR gate. So it obeys that. So these are also few of the laws that the logic circuits also obeys. And along with this, we have the De Morgan law as well, mean x plus y or x or y whole complement is equal to x complement dot y complement. So it means if we have the AND gate, hope that it is visible, let me write it again here so that it's become easy for you. X or y whole complement is equal to x complement dot y complement. It means that if we have OR gate with two inputs x and y, and if we connect a NOT gate in the output of OR gate, we will be able to get x or y whole complement. So it is exactly equal to this circuit with AND gate having two bubbles, you mean two AND gate, two NOT gates at the inputs of the AND gate, and here we have x input and y input. It is equal to this one. It is x complement dot y complement. So the functionality of this is exactly equal to this. If you replace this circuit, let me write this NOT gate just by replace that by a bubble. So now this becomes a NOR gate. Okay. So this is a bubbled AND gate. So the function of the NOR gate is exactly equal to the function of the bubbled NAND gate. So this is basically what the De Morgan's law says, or De Morgan theorem says. So Boolean logics also obeys this Boolean law, which is the De Morgan law. So these are the few laws in today's lecture what I have explained. There are few more, but I will explain it later on. Let me write we have these four Boolean identities based on the AND operation, these four identities based on the OR operation, this is one Boolean identity based on the NOT operation, and it always obeys the laws like a De Morgan's law, the associative law, the commutative law, etc. And it obeys these laws based on the AND operation as well as based on the OR operation. So logic obeys all these type of laws. So that's all for today's lecture. And this lecture was just about the identities and the laws of the Boolean algebra and why we are using the Boolean algebra. As I mentioned you that Boolean algebra is a mathematics, and once we put the logic into a mathematics, so it makes our life easy, because mathematics is a very old science and it is very rich in terms of the mathematical formulae, relations, mathematical relation, etc. So it is why if we put the logics into mathematics, so it makes our life easy. As I have given you an example of walking through your feet and traveling the very huge distance and traveling covering the distance through an aeroplane. So it is why we are talking about the Boolean algebra and the Boolean identity. So that's all for today's lecture. Thank you very much. See you in the next lecture. God bless you. Thank you very much. Allah Hafiz.